back. All right, let's pick up where we left from. I don't know why this is pointing that way. That should not be pointing that way. Oh, actually, yeah, what the heck? That should not be pointing that way. Oh. All right, now we can start. Let's pick up where we left from. I basically forgot to turn it on. So on the last video, we built this thing, the new blue robot, which is basically the best design we've come up to so far. And we were trying to get things to move, but we were struggling to do so. And one of the things I noticed was I think we've stripped some of the servo heads. So for example, right now I'm telling this guy here that it should be at 0 degrees, and it's just at some random angle. I think 0 degrees for this guy would be somewhere pointing this way, but you can see here, I think we can move it, even though the servo is locked in position. So that means that we're not transferring any torque from the servo to this leg, and so something's broken. Now to fix that, it's not a big deal. We just need to take off the leg, replace the servo horn, and reinitialize everything. But we've already done it a few times, right? We've done a lot of assembly, and it's getting a little repetitive. You probably don't want to watch it. I just want to fly through it. So I'm gonna quickly time lapse through me fixing that, and then we can get started. Alright, so I removed all of the legs and removed all of the old servo horns. I have them here in a cup. And I've replaced only one leg for now, the rear right leg. So we're going to take these one at a time. The reason why is because I think one of the places where we strip the horns is when the robot first powers on. And we don't have a good way to sense like, oh, be gentle when moving the knee if the hip is in a certain position or something like that. So we need a better start sequence so we never stress our servo horns unnecessarily. So that's one. The other thing is like I learned that these jigs that I made to initialize the servos, these work great when the servo box is not attached to the torso. When it's actually attached to the torso and you place this in there, it locks in place because the torso here keeps it from you being able to remove it. So good lesson learned, another thing to improve, and yeah, these will need to be modified. The other thing I was gonna say was that I did find another iPhone, so I use cameras as iPhones. You're in an iPhone right now. So now we have two iPhones. I'm gonna be able to basically record my screen and also record the robot as it moves. So as I code, we can see everything happening in one screen. So hopefully that works. I do wanna say though that we're getting to the point where, because my background is in mechanical engineering, and I can do electrical, but software is it's an area for improvement right now for me. So we're getting to the point where I'm gonna start making more mistakes, and I'm just gonna. When I first started these videos, I said I would keep it real. I'm gonna record every single minute just so you can see, the lows and the highs, and I'm gonna keep doing that. I think that, when I try to hide things and I try to make things higher production quality and stuff like that, it actually slows me down a ton. So, I could have probably, built this way faster if I wasn't concerned about like, oh, how is this gonna look when I record? Or I wanna make sure like I don't look too dumb when doing that. I don't wanna worry about those things anymore. I'm okay with looking dumb. I'm gonna show you exactly me trying to figure this out. I'm not saying this is the best path, but if you know of a better way of doing things, I would really appreciate if you could leave a comment, because trust me, I wanna like thank you for it, and I wanna like really consider it. Anyways, let's get to work. All right. Actually, okay. So many new things happening, guys. New haircut. I don't know if you noticed. New drink. We're not drinking 7-Up or Sprite anymore. Now we're doing Soleil, which is like a sparkling water with flavor. No more 7-Up, no more Sprites. Coca-Cola never sponsored this channel, so we have to keep changing the drinks. And there's the new camera. So how's that? So there's me, and then there's the robot, which is just down here. That's my hand. But now we have 2 cameras, and then we have an awkward little empty space down there underneath the robot. I don't know what to fill that with. Maybe another camera. I don't have another iPhone, you know. Or maybe just like a banner. Subscribe. Before we got started, I wanted to point this out. So I found these. So obviously we have an issue with the mess of wires that's like on top of here, like all these wires here on top you can see, and I obviously want to fix that. And you know, we had a video where you talk about making a power PCB, and that's one way of doing it for sure. It's just taking a little longer than I like. And another way of doing it, since you know we already have an Arduino and hooking up servos to an Arduino is really like a pretty common thing to do, is we can buy a shield, an Arduino shield that that does exactly that. And Adafruit seems to have one here. So the shield you can put on top. You can connect 16 servos. It has its own power supply. They don't rate the max current. On the forums, I found someone saying like maybe 3 amps, but not continuous. It comes down to thermals really. So that could work. The only hesitation I have is that if we do these, we need to move to I2C and use the Adafruit library instead of using the servo library with PWM. So I don't know, it could add complexity. It can make things a lot neater. So it's very tempting, and yeah, it's only $70.50. I did try to shop around for other shields, and I was surprised I couldn't find others. But this shield also comes with a bunch of other neat features, like you can set maximum PWM ranges, the hard maximum PWM ranges here, so you know you'll never hurt your servos or your legs like the way I just did. So that's interesting. But yeah, other than that, I just want to point that out. I haven't ordered yet. I feel like if we keep going, we keep getting distracted. We just need to focus on the goal, which is walking. And I guess that's the other thing I was gonna say. This video right now, today, well not today, but this video, maybe today, we're gonna get this thing walking. First step, it's gonna walk across my living room. I don't care how long it takes. Maybe this will be our first 20-hour video, if that's what it takes, but I'm gonna get it done. So yeah. Anyways, let's open our Arduino IDE. This is what the Arduino IDE looks like. This is in the code I wrote. Let me open. It's weird because I keep my code on GitHub, so I use VS Code for that. But then the Arduino, you cannot upload to the Arduino from VS Code. There's no extension for that. At least I couldn't find one. So I keep going back to the Arduino IDE, which doesn't have version control, doesn't have all these things, and I have to manually copy it to VS Code, upload it, and so on. But anyways, I'm gonna go ahead and connect the computer to the robot, and I'm also going to turn the robot on. Alright, so turning it on in this case is not a big deal because we only have 3 servos connected, but it has its own power supply, so we're never underpowered, and the Arduino is never going to trip, and so on. There are so many wires on my ground now. And this is the code I wrote on the last video towards the end, where I was like, I wish I could share my screen. It's really simple stuff. We just initialize the servos using the servo library, kind of like formatting, create servo objects. We create the objects. Then we attach the objects to pins. So these numbers are digital pins on the board, just PWM pins, 13 all the way to 2. And then I wrote comments here so I know what each of them means. And then to move a servo, you just servo, the number of servo you want to move, right, and the angle you want to move on. So of course the first thing I do is also, I don't think you need to call them servo 13. I think you can call them Actually, let's try this right now, but servo 13. There's like a replace with rear right shoulder, or R shoulder. I think that yeah, you can call him that, and I think that works. Let me verify it. Yeah, and so now if we want to move the rear right shoulder 45 degrees, we upload this. Yeah, like I said, we upload this. And it should move. Oh! Oh! Oh no! Alright, we broke a few more things. So we broke the Arduino board, took the blank of the head, and the screws that were connecting that to the robot have broken, sheared off. Other than that, we seem to be doing fine. Oh my god. Alright, well maybe we won't move the shoulders. Let me just put the shoulder back to 90. But yeah, you can name these whatever you want. That's the second time we've fallen, I think. Alright, no more falling. Anyways, okay, so that's basically it. And what we need to create is a safety envelope, quote unquote safety envelope. I think we did this for last time for the... So we're for when servo 1 is at this angle, servo 2 can be between these two. So when the hip is at this angle, the knee can be between these two. So that's what we need to create. There's another way of doing this, which is doing it on shape. Now that yeah, on shape. That's what it's called, right? Yeah, do it on shape. Now that we have like those installing jigs, and our servo installation and initialization is good. In theory, we could do this on shape, you know, trusting that everything's installed perfectly. I'm just gonna do it in real life just because maybe I don't trust that last part where everything's installed perfectly. This is decent. It's less sweet than a Sprite, so I don't drink it as fast. Yeah, so we're literally gonna like cycle through all of these things where I type one angle, upload it, and so on. Maybe I can just time lapse this because it's gonna be repetitive. So here we go. All right, so first of all, I'm gonna get rid of all these servo lame names and replace them with better names. All right, so now our naming convention is way better. It doesn't suck, and so now we'll start. So we were initializing legs for standing. We really can get rid of that. That was just like something that I like kind of like brute force myself to just to see like, oh, okay, what would be like a decent stand? In fact, if we run this code, I guess it's already running. It actually doesn't look like a decent stand. I don't know if we broke something, but that doesn't look good at all. So, all right, so maybe we start here at 45. And what I'm gonna do is I'm gonna split these here like so. And we have to do these for the right side. I mean, we can just calculate it for the left side, I guess. I call this safety envelope B2, and it's gonna be like right hip, and then right knee min, right knee max, right? So at 45, which is what we're at right now, the hip is at 45, the knee is at 130. I don't think, let me just check. So higher numbers is, oh, what the hell? Higher number is clockwise. And higher number is counterclockwise. Yeah. So I wouldn't take it, I would say that's the max. Right? So what you should be looking for is you should be focused on these joints here. All right. So wait, and what we said higher is counterclockwise, CCW, and then obviously lower is clockwise. And so we want to go clockwise now. We can take a big step here, and we just want to make sure we're not. We want to basically find the next position where things can clash. And we'll get much faster as we kind of like get comfortable here. I don't know why it does that thing where the shoulder is like moving so much. I think that's the minimum, 20 degrees. All right, so last time we were doing 5 degree steps, so we can do the same thing here. And like I said, there's probably faster ways of doing this. You can probably do it on CAD. I will feel more comfortable knowing it's 100% correct. If we do it like so, like in person. When you do the things with your real equipment, it accounts for, you know, all the defects, shortcomings, things that are not according to CAD, so on. So that's why I prefer doing it this way. And yeah, the robot's on the floor just to minimize the distance whenever it trips and fails, just to try not to break things. All right, we're doing 50 now. Okay, that should not be happening. So the rear shoulder. I don't know why it's cycling this. I can't think of a reason why the shoulder is cycling like that. Anyways, really odd. Our previous max here was 130, so Well, again, I really have no idea why our Arduino keeps like cycling the shoulder like that. I have no clue. I mean, I could remove the power to that shoulder. It's very annoying, so maybe I should just do that. But it would be nice to have an explanation, you know. Let me just Google this real quick. Apparently pin 13 is not a PWM. Pin 13 isn't a hardware timer. Really? I searched on the hardware. I mean, well, I guess have off-branded boards, but I thought they said they were. Looks like there's less pins that can do PWM than I thought. Arduino Uno, PWM, servo. Yeah, it looks like the servo might be already handling these. The forums are talking about the grounding issues. This is not it. Okay, how to stop random servo movements during reset. I think this, well, it's not because of anything you're doing or not doing here as well. apparently that maybe the Arduino bootloader takes too long. I don't know if I buy that. Okay, so it seems like Arduino sometimes during initialization will basically send different PWMs to what we have here, and it's because when the bootloader first starts, it doesn't immediately run these. Instead, it sends something equivalent to 0 or something close to that. I'm surprised. I mean, I'm surprised there's nothing for these because it seems like such a basic thing. Let's see, Arduino servo library. My servos randomly move when I initialize /power on the board. How do I fix that? Let's see if ChatGPT knows. All right, so ChatGPT says this happens because the servos receive power before they receive any signals, and it's suggesting adding a delay before initializing the servos. How is that going to help? Let's see, initialization. Before calling servo, use servo write. Oh, really? Let's try that. I want to initialize the shoulders here. Sorry guys, getting a call. Let's see if the camera, all right, camera came back. All right, let me, okay, let's see if, I'm gonna hold the robot just in case, but let's see. No, still moved. I don't think that did it. Well, okay, now it seems to be working. Do we trust this? Proceed as if everything's fine. Oh, it seems. It really seems to work. Alright, the ChatGPT solution did not work. And we fail again. Okay, great. That's the third time falling with the same issue, so now I feel very stupid. Alright, the other thing is it recommends adding a delay. We can try that. By the way, we've broken this horn, so we need to repairs. Probably in one of the falls, honestly. That was embarrassing. But let me just try these. I mean, that's the thing. It feels like it's fine until then it's not fine. Yeah, see, that's not fine. I mean, there's one way to work around this. It's like basically like, oh, just never let it touch the ground when initializing. But you know, what if like these random servo movements actually break the knee, the horns and stuff like that, right? Like we cannot live with this. When you attach a servo, it moves to its default angle of 90 degrees. However, if you do a servo right before the attach, then it moves to that position when attached. I suspect what is happening is that the initial twitch is being caused by the move to 90 degrees. No, that's not what's happening here. I think the issue is that the servo power source and the Arduino power source are enabled at the same time. Then there will be about a 60 millisecond boot up time for Uno. Oh, this guy might be onto something here. If the servo power up is enabled and boot up, then I think the startup jitter will be later. Okay, so basically this would only happen when I'm connected to the Uno, but do I buy that? I don't know if I buy that because the only cable connected to the servo is the PWM cable, and I don't know if that's enough to. I don't think that's enough to basically to power the servo. And also, if you were wondering, no, I don't think this cheap buck converter has this function to connect to the Arduino. There's a lot of threads on these. People seem happy with the solution. Anyways, I do need to fix the knee that just sheared off. That won't take long, but just very annoyed at this. It's a very dumb way of failing. See, that shouldn't happen. Oops. That was gonna destroy itself there. That doesn't look like 50 to me. See, that should not happen. Oh. We set it to 0 and it's up here. What happened here? Yeah, okay. I think we've stripped everything. So more repairs. It's fine because I did print extra servo horns. I'm just a little puzzled as to like how we're gonna fix this. Because yeah, we cannot have these random movements like that. Okay, and the solutions that people have online are not really, they're not real solutions here. Maybe that Arduino shield that we were talking about earlier would fix this. Oh, this is a new thread 8 months ago. All right, so it seems like, so I don't read any good solutions. All the code solutions people proposed we've already implemented. Those didn't work. Some people are suggesting making sure the servo is initialized fully before powering up the servos, but and if that's the actual issue, it will fix on its own if we ever basically run these without being connected to the computer. It's just very frustrating. Yeah, Arduino, don't use USB as power. Turn on USB power supply. I don't think that's. Yeah, all the solutions people were talking about do not help. Basically, I'm just reading forums here. I don't know how to fix this. Okay, this guy's code is very similar to mine. Pin mode 5 input. Oh, I'm not initializing the pin. Oh, I guess he's doing other stuff. Debounce and maintain the current state. No idea. I would also ensure that it lays long enough for servos to reach. You call servo X repeatedly when no button has changed. Each call turns off interrupts briefly while the servo value is being updated. This happens maybe 40 times per second and maybe messing up with the servo timing.
that's not relevant here. Arduino EEPROM. No, I don't think that's it either. Okay, so I'm very tempted to say that this has to do something with the Arduino Uno not having enough PWM pins, and whatever solution it's doing with through code it's not working. Or it's like failing somehow. 0 clock. Yeah, so pin 13 where we're connected appears to be the 0 clock. Is pin 13 on the Arduino Uno. Oh. Let's see if ChatGPT. Oh. So it says the pin 13 on Arduino Uno is also tied to the built-in LED, and it often starts toggling during boot up. So when you power on the Arduino, that pin might be pulled high or low briefly before your sketch even starts running, causing random signals. Okay, that could explain it. I am which out of so let's that could explain. So maybe it's the pin 13 that's not good. There's 13 to 0 out of the Arduino Uno digital pins 13 to 0. Are there others that are also not suitable for servos? Good question. Here's rundown. If I'm not using the 0, I am uploading. Okay, so maybe we can move pin 13 to 0 or 1. I am uploading code via USB. Oh, and not using the serial monitor. Would there still be interference in pin 0 and 1? Okay, so it looks like 0 and 1 are also not good. So even though the Arduino Uno has 14 pins, only 11 are actually proper. That sucks. So we might need a different solution then. I'm gonna grab another drink, go to the bathroom, I'll be back. La Croix? La Croix? La Croix? Beach plum flavor. So maybe the Arduino Shield we talked about earlier would work, but I think there's probably some unknowns with moving to I2C. The other thing I have in mind is that we have another Uno. I think those two can be linked together. And that could work. Or we could move to an Arduino Uno, Arduino Mega with more ports. Of course, bigger board, it's kind of like a bad solution. Also, nowhere here does it say that this is connected to an LED. Let's fact check ChatGPT. Digital pin 13 LED. I mean, maybe. Well, what about ICSP? Oh no. Man, this sucks. How are we supposed to walk if we're missing one servo? I mean, the other solution here would be like literally to always take off pin 13 on startup, and then and then remember to connect it again. I don't know, like what else could we do? Because PWM over. Can we use the analog pins as PWM? Pretty sure no. Maybe yes. Arduino Uno control servo PWM or analog pin. I feel like oh. Apparently this could work. I'm down to try anything. I'm desperate. I feel like this is kind of dumb. Can I use the Arduino servo library to control a servo over PWM using an analog pin? Nope. So someone lied to me. How would I set up an analog pin to be used? I feel like ChatGPT is contradicting itself. It's like, yeah, you can do it, but technically it wouldn't be the same thing. Okay, so touch A1. Touch A1. Oh, it seems to have worked. Let's try it. Let's try it. No way. No way that's working. Oh. Whoa, we're back in business, guys. That's crazy. That's crazy. That's so good. I really thought we were blocked here. Actually, okay, let's run a few more tests. Let's make sure this is a real deal. Yeah, I mean, it's not drifting anymore, right? That's what we wanted. What else can we ask for? We fixed it. All right, so I'm gonna replace the horns once again because we stripped them by crashing onto the ground. Yeah, and then we'll keep going with this safety envelope. All right, everything's fixed. We have a new drink also, Soleil pineapple this time. I think the last servos were not on all the way, and that's why they stripped so fast. So I've given these a little extra tightening, so they're tighter. And well, the Arduino is broken now, which is a shame. So we will have to print a new torso, which is, you know, takes a while, and there's some assembling involved, and I have to redo the wires and all that stuff, and that sucks. So I'm in no rush to fix that. But you know, it'll happen at some point. And so, anyways, we can continue our work here. So last time we were at 65. So we're at that angle, and now we're moving on to 70 degrees. And like, we should upload now, and nothing is gonna jerk. Okay. See, it's perfect. Such a perfect robot. Anyways, that was the first for me. I feel like I learn new things every time I touch an Arduino. That's not actually moving the way I... Okay. Let's go back to 65 because I am kind of doubting that that was our max there. Yeah, 65 is on the max here. 50 is on the max here. We can go lower. Probably everything, something was already broken. Yeah. Okay, so I'm gonna redo our work here, which I know sucks, but I mean, I'm gonna start where I think things are okay, and again, maybe we just time lapse through this, but. I know what's wrong here. I apologize. It's my fault. I've initialized the servo knee wrong, so I didn't set it at the right angle. I forgot to set it at 90 degrees, so I'm gonna go do that right now. All right, it's fixed. So the issue was that on the last video, I came with this big brain idea of like having a separate Arduino to initialize the servos during assembly. And so all you have to do is change that PWM wire to different pins depending on which servo you're initializing. I forgot to do that, so I set the knee to the same as the hip, so the knee to 0. Now that's fixed, and so everything should be fine. And we can proceed. Basically, start from scratch, and moving very slowly here, guys. Very slowly. And if you're watching these and you're like, "Oh, why is this guy doing these?" Dude, why don't you just figure it out on your own instead of like making videos? Then it's because you don't understand that I actually like making videos. And yeah. Totally, it would be faster just to do it on my own, but I actually do enjoy making these videos. Okay, it's still not moving as I would expect it to move. Didn't move at all. Oh my god, Mac. Lower numbers should be moving clockwise. These should be coming down. Interesting. I'm not seeing the Arduino here. Maybe I broke something else. Alright, looks like a bad servo connection would be my guess. looks correct.
Huh. I'm not sure what's going on here. Oh,
I forgot to turn on the robot, so there was no power supply. That explains a lot. Basic mistakes, guys. Just making basic mistakes. All right. That looks like that doesn't look safe. All right, now we're moving in a way that makes sense. Okay, now things make sense. Now we can get to work. All right, we've completed mapping the safety envelope. So these are the angles. So based on what the angle of the hip is, these are the angles that the knee can take for the rear right. And it's the same for the front right. We do have to take into account conditions where the two legs can clash, which is not accounted here. And then we can translate these to the left, which is some simple mirror shape rotation, big brain stuff. So really, I think the next step, we can now add all of the legs. But you know, before we do that, maybe just for fun, we can maybe we can do like a loop thing. We can like create some code to loop around the legs. So today is October 25th, 2024, and we want a loop, you know. So this is what I was saying, that how I normally save my code. All right, so basically I'm gonna create a new file here called loop, and I wanna build on top of the previous file here. And what I'm gonna do is I'm gonna ask ChatGPT. So I'm in VS Code. I'm using this extension called Double. I used to work here, so Double. And so what Double does is it brings VS Code onto your IDE. In this case, VS Code. Sorry, it brings GPT, Claude, all these LLMs, all AI to your IDE. So here on the right, you can see I can choose which model I want. And I can do things like I can pass the code and say all the code is here. So now the AI will see it, and I can tell it to basically loop using these things. So please help me write a code that loops the RR hip and the RR shoulder servos based on the I'm gonna clean up the code, the titles here, so it's clearer. RR knee angle min. Based on the min and max angles, so we do not want to step outside of the angle range, as these will damage the servos. The angles are as follow, and I want to copy and paste one at a time, just because like I think copy and pasting from tables sometimes messes things up when going to text, but I think this will work. I think Claude, I'm using Claude 3.5 Sonnet here. I think we'll understand. And so Double generates the code here. Here's the code, and one of the neat things about Double is that you can basically click on this thing here. So I'm not even gonna copy and paste. I just click apply, and it adds the code that we need here. Now, this is basically what it added. Actually, let me do that again, right? So it highlighted for us the sections that it added. So it's here in red. And it's funny, right? It says, let's get this bread, or should I say, let's move these servos. So it has a personality. I've set this up, like you can change the personality of Double as you see fit. So for int hip equals 0 to, okay, so the whole entire hip range, right? Hip right, hip angle. Yes, calculate knee angle in index. Hip. I I see. Oh, okay. I see how it's doing it. Oscillate knee between mix and max. Okay, I see. Okay, this is one way of doing it. So I think that would work. Just looking at the code. So it's basically gonna go the full sweep of the hip, and for each position of the hip, it's gonna move the knee. Let's upload this and let's see it. So I'll move the camera so you can see it. I think it's pretty good. It's been a while since we had, properly working legs and servos, so I am so happy to see this. This is great. You can see that as we reach the extreme, the range of motion of the knee gets shorter compared to the beginning. That's cool. Now I could add other legs, or what I could try to do now is basically try to map out a step, right? So what would a step look like? By the way, well, there's basically no way to stop it right now. Just keep cycling. So we can actually tell the clock here to make sure it only loops once and then it stops. Alright, so those were the changes. AI is just coding for us. We're gonna upload these, and now it's only gonna run once. And now also notice that the shoulder has not jumped or done anything, anything jerky or anything since we moved away from pin 13. So that was the solution. That was really good. Cool. It didn't move. That's neat, man. That's really cool. I'm gonna eat something for lunch. It's 5 p.m. and I'll be back. And I think first we'll model something that looks like standing, and then after that we'll try to do a step. And yeah, that makes sense. We might walk tonight. I'm not sure. Depends what time my girlfriend's home. All right, I'm back. We have another LaCroix. I hear this is the official drink of San Francisco. And so, all right, so let's write down what we've done so far. So first of all, we have that Adafruit Arduino shield that looks interesting. To do fix servo horns. We've kind of like done these already. I've done it for one leg. Second, build servo safety envelope. So we know, I'm calling it safety envelope. This is basically that spreadsheet that we just built. So that's done. Next, do a hard-coded stand. And after that, hard-coded walk. And if we can do these things on this video, I'll be very satisfied. So I'm gonna do hard-coded stand right now. So this is the code we had before. We don't need a void loop for a hard-coded stance or void loop. Void loop on Arduino, just it's a default loop, right? So this is how the default Arduino files have a loop, and it just kind of like runs forever. For a stand, we can kind of like just figure it out here. So we can do RR hip right, and it's like probably somewhere like 50, and then we do RR knee right, and let me look here for 50, somewhere like maybe like 110. So let's start there. So I want to push this code. I think you guys can see, right? You guys can see the camera. Oh my god. Wait, what? Global variables? No, that makes no sense. Man, I think the Arduino was running for too long or something. It's all nonsense. By the way, I don't want to hype things too much, but oh my god, it's running on the loop. See, the board is not coming up on my serial monitor. Serial ports here. This happens sometimes. It's okay. I just restart Arduino and the IDE when that happens. I was gonna say I wanted to do a public display in San Francisco with the robot. I'm actually next week. It's pretty cool. Since posting these videos, people reach out. They're like, "Oh, this is what I'm building." I've met a couple guys building robots locally. I've also met some people who want to sponsor the project and offer like PCBs and stuff. That's nice. And the other thing is I think I want to do like some sort of public display. So I'll take the robot to a park in San Francisco and have it interact with people and start building some sort of following that way, and eventually turn that into a YC application and try to build a company around these. I'm still starting on it. Maybe we'll do a video where I just try to build a business case for it. But that's kind of like where my mind is right now. All right, now if you see the robot underneath here, right there, so that's what the stand would look like. So I think the knee needs to come a little bit higher. Somewhere there, even higher maybe. I think that's a good hard-coded stance. And then basically, well, here I would write hard-coded stance. Stance? I'm learning English as well. Yeah. Stand. The other thing I was thinking about was I was thinking about these kind of random, because again, I watched that Wild Robot movie, and I was like thinking, I think one of the big contrasts between the robot and the animals were that the robot was all about tasks and goals, and the animals were just about existing and having fun. I think humans are somewhere in between robots and animals, of course. But I do start to wonder, what is the evolutionary purpose of fun? And I had a little conversation with ChatGPT about this the other night, and it was saying that fun is supposed to encourage good habits and things like that, healthy habits. But of course, if you fast forward to the present, right, where it's like having fun can lead to a lot of destructive habits, kind of like scrolling TikTok all day, right? Like that can destroy you, dopamine cycles. So I didn't believe yeah, I didn't really fully bought ChatGPT's argument. I almost feel like having fun is a way of introducing randomness to evolution, right? It's like, oh, why did you I don't know, went up that hill and like, you know, build your house up the hill just to have fun, you know? Does it look fun, look enjoyable? I mean, that might not be the best example, but I've been thinking about having fun. I would argue that in a lot of ways we're removing fun, and that might just be like my idea of fun. I think my idea of fun involves a lot of risk taking, and that's not necessarily true, right, for everyone. I like to go surfing, I like to go snowboarding, I like to go hiking mountains, I like to, you know, I like driving cars, and these are things, you know, like I said, like we're probably not gonna be driving cars anymore in 100 years from now. It's like less fun, but we'll have more TikTok scrolling and VR and all these things, so more fun in a way. But yeah, I do kind of wonder why living organisms seem to like having fun. You know, computers do not have fun, and it's like, is having fun like part of having a personality and like will? I'm sure there's like a lot of literature in these that I could go and write and read. By the way, the background keeps changing. That's just Mac, I think, because of the time. Anyways, rear left hip. Front. Wait, what was it? FR. Front right. Yeah, rear right, front right. And now we have rear left, and then front left. Anyways, if you have any opinions on what's the purpose of fun, let me know. I know it's kind of like a nerdy question because it's like to just have fun, but I see a lot of quote unquote smart people on Twitter dunking on simpler people who like having fun, who like dancing, who like listening to music. This you know, a lot of Twitter talks about these traits as like low IQ traits, and I just don't necessarily buy that. Although I am someone who likes to have fun, I like to listen to music. Can be very simple-minded in that sense. For the left stuff, I just translated this by 180 degrees, right? So the right hip is 50 degrees, initialized at 0. So from its 0, it's like 50 degrees. The left hips are initialized at 180, so minus 50 degrees, so 130. And the same thing for the knee. So I think that should work. So if we were to let me create another file, and I'm uploading all of this stuff to GitHub, by the way, and the code is public. You can go and see it. I'll link the repo. I'll link the repo on this video if you don't know where to find it. Wait, I can't see the code. It's like, yeah. You can also download Double for free. This extension I'm using. It's free for, I think, 30 days, and yeah. Yeah. Anyways, let's test this stance. Let's see how it stands on its own. So for that, I need to put back the legs, all the legs. So let's go do that right now. And I'm just gonna time lapse through it while listening to music, having fun. And then we'll be back when it's standing on its own. Once we have that, we'll get started on walking. Sounds like a deal? All right, all the legs are on, are attached now, and still broken here. It's kind of awkward to connect the USB, but power is on. And now if we flash the firmware that we just wrote, they should all be standing properly. Or I did something terribly. So let's see what that looks like. So I see the rears standing correctly. And the fronts are struggling a little bit. So kind of suspicious. Let me just loosen out the joints in case there's too much friction. Oh. It's I've been finishing torquing the joints by hand because it's very easy to over torque, I think, with electrical tools. So let's do one side of the robot at a time. So first the front. I want to make sure that our hip has initialized correctly. So if we set this to 0, the front right hip should come up. And it's not doing it. Front right FR hip. FR hip 0. Okay. Why is it not doing it? Let's see what I missed. So power is on. Connections seem fine. Servos are not fighting. And it's 0. Okay. What about 90? FR hip right. Am I missing something obvious here? FR hip. They do have power, so I can move it. So if our hip, I'm just verifying the wiring here, make sure I didn't mess anything up. I mean, I doubt it, but our hip. FR hip. Let's go into 5. FR hip 5. Is that correct? FR 6. What is 6? I see. Looks like I've accidentally flipped these two. No. I'm trying to just figure out what went wrong here. Just troubleshooting by changing the angles manually. Okay. Interesting. 180. Yeah. What about these guys? 70. So FR hip seems to be trying to move something on the other side. So maybe we kind of messed that up. Last time, the other night, I just wrote things on paper on what goes where. So front right hip is attached to 6. Front right hip attached to 6 is what I have here. Front right hip. Okay, let's check the wiring here. This would be a very dumb mistake to make. FR hip wire attached to 5. Okay, FR hip 5. FR hip 5. What's attached to 5? Knee. Oh. Let me try this. I see the issue. It's a wiring issue. So let me just fix it here. So that beeping, it's indicating. I'm gonna turn it off. So that beeping, it's from this guy here, the voltage monitor, and it's just indicating that the battery is drained, or I mean, it's kind of getting drained. So I'm going to replace the battery with a fresh pack, which I actually do have, and so replacing the LiPo with a fresh LiPo, and also while I do that, let me just check. Looks like I made a slight wiring mistake, and so I have my pins incorrectly set up, which is not a huge deal. I can just fix it via software, and it doesn't seem like we broke anything. But the battery pack it's not hot, it's lukewarm. So we were draining it just now, and that most likely just indicates that the servos were pushing against walls or stuff. So the servos were fighting based on my command. This thing is very loud. Alright, so this pack is, all the cells are at 4.10 volts, so which is almost a full charge. So now, actually, yeah. So now I'm just gonna jump in here and double check the wires and that they actually go where I want them to go. So the front right hip is here. Front right hip is actually going to pin number 5. And the front right knee is actually going to pin number 6. So the front right hip and knee were mixed, looks like it. But now let me just verify everything, just to make sure. It won't take long, and this way we don't damage anything. So the shoulder, front right shoulder is at 7, which is correct. Front left shoulder, left shoulder. Is at 4, front left shoulder is at 4, that's correct. Front left hip. Front left hip. Is at 2. Front left hip is at 2. So the hips are, the hip and the knee are mixed up. Front left hip. Front left knee now is at 3. Alright. Now let's double check the right side. Sorry, the rear left shoulder is at 10. Rear left shoulder is at 10. That's correct. Rear left hip. It's at 9. It's correct. And the rear left knee is at 8, which is correct. And we already know that the rear right joints are correct because we were using it earlier. So let's modify the code and get a fresh battery in there. So let's see, the modifications are FR hip is actually at 5, FR knee is actually at 6. Checking it on the paper, and the front left FL hip is at 2, and the FL knee is at 3. So slight modification there, not a big deal, software fix. So that's fixed now, should be fixed now. And so we'll try this again. Let me see if I can upload the code before putting in a battery. Just so when the battery's on, we're not doing anything crazy. Uploading. We're done uploading, and now I'm gonna put a fresh battery in here, which is super simple. You just come in here and strap this on. I actually need the voltage thing, voltage monitor. It's gonna be loud, guys. You've been warned. Alright, strapping it with Velcro and connecting it to the buck converter switch. I imagine the switch is on now, and we're back in business. And so let's try. Okay, so first of all, look at the stance there on the front here. It matches the rear now, right? And so now that's good. So let's try the other side also. Rear left should mimic rear right, and it does. And now front left should mimic the same thing, and it does. Okay, a little off to be honest. We can trim it. It's kind of like this is how it's trying to stand. So it's a bit crooked. And some of these horns are not holding torque. I wonder if I put the right horns. Those should be the correct horns. Yeah, a lot of the actuators on the left side here seems to be something that's wrong, because like look, and I think you can see it on the camera. Yeah, it's like actually this one seems, yeah, look, I should not be able to move this with my hand. And like in this case of this one, I should not be able to move this with my hand. So it's not on all the way. Which is odd because they do look on all the So I'm getting a bit tired of having to deal with servo horn issues. So I'm gonna print new servo horns, but I'm gonna tighten the fit. So there's more interference with the servo pinion, and there's more engagement. We shouldn't be stripping servo horns like that. That should not be a thing. That should not be an issue we have. So if we just go to this file, so these are the servo horns, and so the issue appears to be here, this fit here. So that's a 5.8 millimeter. They're both the same, probably, yeah. So we can bring it down a little bit more interference. It's gonna be tighter going in. One of the hard things is to figure out when they're deep enough. When you're installing them, how deep they are, or if you should keep torquing them. So if you mess up the installation, which is I think what I just did, it's, you know, you kind of like, you have like improper engagement, and it's way easier to basically strip off the little bits that are engaged. So let's try that, and let's print fresh samples of these. And unfortunately, this might take a little bit. It's not as quickly as I would like, but let's open Bamboo here. But I mean, yeah, we need to finally fix this once and for all. I don't want any, like, I need that robot to be very reliable. I need these servo horns to not fail. These are the old servo horns. I'm gonna bring new specimens. I'm gonna print only two sets at a time, just so it's faster. And yeah, enable support. I'm also gonna increase the wall loops here to 4. And so if we slice, actually, and then let's just rearrange here to 1. So if we slice this blade, see, it's a half-an-hour print. We might as well get started now. I'm gonna print on, turn on the 3D printer. I really cannot imagine doing this without having my own printer, because like I think like every single day we run into an issue and we have to print something new. So imagine if you were waiting on a supplier to print and ship, and it's like that could take a long time. So I'm glad we have these here. We had a little G-code interference there. 34. All right, send it in. So now you're gonna hear the printer in the background. Now, just because the left side, and it's suspicious that both of the left sides are wrong. I would have imagined both of the front sides are wrong, because those were the ones that I got wrong before. But in the meantime, it doesn't matter. We can just keep going. We can just try to code a. Yeah, this is so awful. And you know what? I can tell it's wrong because of how much it moves here, how much blade there is. Hard to show on video, but I can see it. Anyways, let's focus on the right side for now, and let's try to walk on the right side. And then I guess later on I'll come back and in half an hour I'll fix the left side. So let's assume this code is correct. And let's also clean up the rest of the code, because the attachment functions were incorrect in our loop here. So we were to, yeah. Okay. So now the next step is to mimic kind of like a step. So we're gonna have a step on the rear ride or the front ride. So I'm gonna talk to Claude and be like, and see if Claude has any advice here. Thank you. I'm always nice to the AI. Next, I think the technical word for this is gait. Right, gait. Next, I want to code the gate or the robot taking one step. For now, I only want to do this for the front right leg. So the FR hip and FR knee actuators. How would you recommend that I go about this? I can give you angles of roughly what the maximum and of roughly what the walking angles will look like. All right, let's see what the AI says. The walking angles, okay, for example, just drop the angles. Okay. All right, so let's try to figure out what angles would make it look like it's walking. And for that, I'm just gonna hard code stuff, right? So we said we're gonna do these with the front right, and so let's focus the camera on right. And so if that is right now, if that is, sorry for the with noises, if that is standing, what would walking look like, right? You gotta actually I guess dog walking. It's basically you're looking at these and these. Like a chill one. Let's not go crazy. And so maybe the hip goes forward to 90 degrees. And we need to make sure, what's the safety envelope for 90 degrees? 90 degrees, 125 to 160. All right, that should be safe. All right, one thing is that when I don't give angles to the other stuff, if I just let it drift, it kind of goes crazy. So I'm gonna hold the rear right to these angles, the standing angles, just so we don't damage anything. If we haven't just damaged something, we might have just damaged something. But no, it all feels solid. Yeah. So. All right, so this looks wrong to me. The knee needs to come up. So again, I'm just looking at my safety envelope here and see how far up can we bring that knee. Is that enough? I don't know if that's enough. Yeah, this might be a little harder than I thought, but I think it's just trial and error. What if we push it a little bit? Push the envelope. Yeah, because if you're looking at the ground clearance, I wanna put this thing underneath the robot here. So if I'm looking at the ground clearance, basically barely during the ground there. So maybe our stance needs to be taller, higher, so we have more clearance. So I might modify the stance a little bit. 70. Oh, typo on my end. Yeah, so maybe if that's our stance. It's like I'm struggling to. I've never thought of what a dog gait would look like. That knee might be trying too hard. Okay. And then we had a delay of a second. And then we go back to FR hip, right? 50. And I'm just guessing, guys. There's no science here. Just guessing. For 50, 150. Let's see. I think if I put this in the loop, it will loop through it. Again, not sure. Our delay might be too long. It's not really doing it. Oh. Arduino ID delay what unit? I think it's milliseconds. Should be milliseconds. Yeah. It moved, but I missed it. Let's try that. I'm gonna initialize it to be first on the stance position that we think we like. Let's see if this. I'm gonna ask the AI for help. Can you make it loop through? It's basically what we already had. Basically added another delay here. Would you call that walking? I mean, kinda, right? I think you can go further back. Feels like we are not really clearing the ground there. 70. I don't know if that will be walking. I guess. What did we have before? I guess maybe that's walking. So it's pushing the ground back as it goes forward, but then as it goes backwards, it pushes it. Like when it goes, when the leg swings back, it's pushing it forward, but then when the leg swings back to the front, it's pushing it forward. So it's like not really going anywhere. So we need another step here, where it's basically FR hip, right 40, and then this knee needs to come up. And for that angle, I mean, we have plenty of room to come up. Delay. Let's try this. Oh, I missed the semicolon. Classic. Alright, so maybe a little exaggerated in the delays there. Let me cut this by half. We want to play it safe. I think that's basically what walking is. I don't know if this will make it crash to the Arduino cable. It might. Yeah, it kind of is. Alright, and I can tell we can still shave time from the delays here. So maybe as we make it go faster, it will feel more natural. Does this feel natural? Let's go even faster. Kind of pushing it here. not super elegant, but I think technically that's a step. I mean, and as I see it in the camera kind of lux, so it kind of like blends it in, and it looks appropriate. Let me trim the delays a little bit more. Yeah, on the stream here it looks like proper walking. In real life it looks a little robotic. Trim it even more. Trim it more. See, now in real life it looks great. In the stream now it looks like it's lagging, it's moving too fast. The camera's connected over Wi-Fi, that's why it's so slow. Touching a little bit to see if anything's getting hot. Oh, the camera kind of stopped working there. Wait, is the camera not working or is it moving too fast? We seem to be, the camera seems to be lagging for some reason. But here, I will show you with these other cameras. Right? That's kind of like, that's walking. That's walking all right. I think that's a step. I would call that a step. Okay, the other camera came back. Yeah, I think that's good. So I'm gonna make it stop now. And when I say now, I don't mean like immediately. It's soon. Walk, you know. Step, you know. I'm gonna push the standing firmware. Actually, I think 70-30. Alright, so now we kind of like know we have a hard-coded step, and it's just one step. Now it's standing. Now the question is, okay, so the question is how do we make it so it's like one step and then on one leg and then another leg can take a step. Alright, so I'm gonna ask the AI. So this is what a hard-coded single step for the front right leg looks like. Our robot is a quadruped. Okay, but I want all legs to move in the right time so we can move forward. How can I do this? Should we define a walking function and call it on a loop for each leg? You know, like a calling function. I don't know if that's how our C code works, but you know, if I was doing this in Python, that's kind of like how I would approach it. For a quadruped gait, we typically want diagonal legs moving in pairs. Yes, that makes sense. It's just my only hesitation is that last time we tried these, like the robot wasn't stable unless it was on on 3 legs. It wasn't stable on 2. It was really stable on 3. So I think we're gonna fall if we try this, but let's see what it's reading here. Boy, it's so it's a step leg. So it's a phase shift for each leg. So your perfect sequence, hip right. Okay. Note that okay, so it doesn't know that it needs to mirror things for the left side. So I'm gonna tell it, note that these angles were made for the right side. The left side will be different because the servos are flipped and initialized in different directions. The left hip servos are initialized to 180 degrees instead of 0 degrees like the right side. The servo range of motion is from 0 to 180, so the left have to move to the other direction. The left knee servos are initialized to 90 degrees, same as the right side. The range is also the same, 0 to 180. But the angles are inverted. So 10 degrees on the right is equivalent to 170 degrees on the left. Let's see if Claude can do this. She's getting into shape rotation territory. I mean, I think this is an okay next step. Oh. It's just not perfect because like the way it's calling things, it won't be a continuous walk. No, show, not that one. No. And like I said, I'm gonna upload all this code if you want to see it closely, but bro, no. I'm just telling it to apply the changes to a specific file. While it does that, let's check on the prints. Almost done, actually, very fast. Has it already been half an hour? I'm like a bit suspicious. Wow, that was fast. Very nice. The other thing I want to code are the safety envelopes to make sure we never ever break anything. Okay, so I'm very tempted to upload this code and see what happens. If we break things, guys, like I think this is the time to be breaking things. So let's see. The offsets are too big, pretty sure. So where are the offsets control here? Let's see. So these are the offsets. So I'm gonna say the delay offsets are too big. What do the offset parameters. Okay. So I think this is still trial and error territory. So let's try these. So I thought it said like the diagonal legs should move at the same time. Don't mind the left legs smashing into the box. Like I said, those horns need to be replaced again. So let's try moving the diagonals at the same time. See what happens. No, there's still an offset. So the code is getting more complicated. I'm basically relying heavily on the AI here to get this right and not break my robot. This is what coding in 2024 looks like. Now that's a symphony. All right. Well, I'm a little nervous to try this, on the ground. Let me get a feel for it. Yeah, it kind of walks. Obviously it's wobbly because like the left legs are not really working. I think it kind of works. I think it's like the only thing is that I don't think that it's doing the stance correctly. So let me push code for it so it stops walking. And of course, we need to think of the software architecture a little bit more. So I want to say, when the legs are not moving, they should be in the stance position. These are the stance angles. Because I think that's not what it's doing. Yeah, face pushback. Okay, let's accept these changes. Let's see it. Basically, you want the stance because it increases clearance to the ground. And you need clearance to the ground so the legs can move. No, that's not it. That's not it. So I'm gonna push this stance again. So okay, so now we're gonna have to see the code because okay, so it's a 3-phase lift the leg, plant forward, push back. No, not like that. I think we need to introduce a phase 4, which happens after the pushback, where the legs just go to this stance position. I think that's how I picture it. Yeah, it's running a lot of nonsense. It's basically just doing it. Yeah, see, it introduces phase 4. It's just doing it exactly what I told it to do. It's not telling me, oh, you're wrong, which would be nice for someone to tell me you're wrong. But okay, let's try that. In my mind, this is perfect walking. I've never made anything walk before. But in my mind, this is what walking looks like. So the printer literally just finished, perfect timing. I'm gonna replace the horns and we're gonna put these on the floor, and whatever happens, happens, man. All right, I think this is it. I think everything's perfect. I think everything's ready. Haven't tried it yet. You're seeing this live. On. So that's the stance now, and all the legs look good now. And so I should be able to remove this box and have it stand on its own, like so. Yeah, you can see it, it's standing on its own there. Pretty cool, pretty cool. Of course, I'm not gonna let it walk on its own just yet, and we're doing this on our trusty Ben's shoes box first. Which I just duct tape. This is a shoe box. Alright, so let's do the same walk as before, except now with all legs. Sorry. So this is our best walk so far. Pineapple drink. Okay, pineapple drink. I've seen enough. We're going to the ground. Moment of truth. Okay, so first I'll show you what it looks like. On top of the box. So this is how it walks. Oh, we took too long, I think. It went to sleep.
Oh no.
Yeah, this happens. Let's get that straight. Alright, so this is how it walks on top of the box.
Okay.
So it's a little robotic.
Yeah.
But I think it works in theory. Like, I've been putting this thing here, and it does the walking thing okay. And Like it basically pushes the ground that way, so it moves forward.
Cool.
So now if I put it on the ground, I haven't tried to put it on the ground. This is the first time.
Okay.
It might fail. I don't know. But yeah, obviously it can't walk yet. Alright, need to refine that. But
That's kind of cool.
it looked like it could walk,
That's so
but I guess
cool.
it can't walk yet.
I think its back leg wasn't strong enough.
The bug?
Yeah, the back right leg.
Um,
Right, because it's not even straight right now. Oh.
It's like, it's almost like it's trying to jump.
Yeah.
Yeah, it doesn't do a good job at staying upright.
Yeah.
Maybe smaller steps to begin with.
Yeah.
Yeah, I need to keep changing that. I don't know, I thought it looked okay. But obviously it's not okay.
Once it gets weight on it, it can't support itself yet. Like the back legs, for some reason.
It also, every time it takes a step, it kind of rotates.
Interesting.
Yeah, it seems to rotate. Yeah, maybe I'll start slower.
That's hard to figure out.
Just trial and error. This was the first trial.
Yeah.
Okay. I'll keep working on it. Maybe tomorrow.
So cool.
It's kind of disappointing. I thought it would walk. I didn't think it was gonna walk.
Yeah, what about the back right leg? Why is it up?
Because that's where I turn it off.
Oh.
Yeah. All the legs are the same, so it cannot be like the right leg is wrong or anything.
But
So,
if that one and the front left one are supposed to be in sequence, why weren't they both up? You know?
wait, what?
If that one,
Oh, I don't know. Maybe I just like it tumble or something. The legs just move anywhere. You can just push them.
oh, they're so like agile.
Maybe I can make it to go slower, but I don't think that's gonna. Yeah, maybe I can make it go slower. Nah, I'll keep working on it over here.
It's cool.
2,000 years later.
Hello. We're back in action. So, drinking Sprite also. So last thing we did is we attempted to walk for the first time on the floor, and that didn't go great. But I'm not exactly sure why it didn't go great. It was kind of like late at night, so I just I just saw it fail, and I said like we'll work on it after the weekend. So we're here. So this is done. This is our to-do list. Hard-coded stand done, and then we're working on this work in progress. And so obviously that was the first attempt to walk. I didn't expect it to go great. It's kind of like when a human is trying to learn to walk. I would arguably say we did pretty good for the first time. But now we're gonna work on making that better. And I think the goal for this video is really to just get this thing to walk across my living room. And on the next video, I want to start testing it in the real world. The first test is most likely going to be a treadmill test, so we're going to put it in the treadmill, and we're going to test how long a 6S LiPo battery lasts, because I kind of have a feeling that we're drawing a lot of current. Just like anecdotally, seems like we're going through batteries really fast, but I'm not sure if we're just doing something really inefficient with the way our servos are drawing current for holding the torque just to stand, or there's something else going on. But it just feels like we're running through those LiPos really fast. Or maybe the back converter is super inefficient. I'm not sure. Yeah, so I think the best next step is to just take a look. So I have this video here. So I obviously recorded everything for you guys, but this is a snippet of where we actually try to walk. And so we can just maybe take a look at these 10 times and figure out what could be improved. All right, so first of all, just let's recall what we've coded, right? So here we can see front left and rear right moving at the same time, same position, and front right and rear left not moving at all, the legs, right? And so it's like kind of like we're walking in diagonals. I kind of think that's wrong. Mostly because, I don't know, can the camera see my legs? Can the camera point to my legs? So I've been thinking about this over the weekend, and you can't really see my legs. That's probably gonna be as good as it gets. All right, so when you walk, take shoes off. But when you walk, you take a step. And first of all, I'm gonna take a step with my right leg, but my left leg, I'm gonna keep it stationary, right? If I was to walk like this, and then take a step with my left leg, it'll be really weird, right? I'll be walking like, we'll see have this side-to-side motion that the robot is experiencing. Now, how we actually walk is like, I'll push forward with that left leg as I stride with my right leg, and then I'll bring my left leg forward, and then I'll push forward with my right leg, and so on, right? So you're actually, so as I take a step like this with my right leg is actually pushing forward, and you can't see my feet, but you should just try it on yourself. I think we all humans, all bipeds walk the same way. And I don't know if this is the right approach, but a quadruped is really just two bipeds in front of each other, right? I think that's how I see it. So kind of like I watched this video on my phone a couple times. Notice that the robot is going side to side, which happens exactly because of what I just described, where it's like one leg is static while the other one moves, instead of one leg pushing forward while the other one strides forward. Watch this. You see how it rotates? As here in this step, first step, as it pushes, the front right leg is pushing back, it immediately rotates to the right, right? I think that's mostly because the rear left leg had a better engagement. Okay, now what happens? Now the other diagonal, and it rotates again. Looks like, okay. Yeah, because if the front left pushes backwards, you want to rotate this way to its right. But then if the rear right pushes backwards, it'll try to rotate also to its right. No, to its left. Right? To its left. So it should counteract. Doesn't seem like it's counteracting. Whoa, it's a lot of rotation. Is it just lack of traction? Here, you can see that rear right left kind of like loses it, and the robot starts to tip. And then very jerky. Again, look, the leg again almost folding here. And it's gonna actuate soon. So we've done a lot of steps. We haven't really moved. We just rotated. And here again, the leg. Look how much that leg folded. And okay, why is that leg folding, right? You can see the servo, or maybe you can't see the servo, but if you look at these, look, this servo horn is like this way, right? And then on the next few seconds, here, the servo horn is moving because it's trying to do the same as the front left, which is like it lifts a little bit before going forward. But as it lifts a little bit, as there's so much weight on that leg, the whole robot goes backwards. Oh, that's painful. Oh, look at that. It's like the camera shakes. Oh, the whole floor shake. That was it was that hard. The camera's in a tripod, so it doesn't weigh much. Doesn't take much to shake it. Yeah, the rotation on every step is a lot. Okay, here it's facing forward. Looks like a clean step. No, I mean, it's weird because it looks like the front left step is doing much more of the movement than the rear right. Look, the rear right kind of stopped there, and then the front left keeps going. And of course it's gonna rotate to the left. It's kind of suspicious, it's kind of weird. Actually, same thing happens on the, here, right? They both kind of go backwards, but I wonder how the weight is distributed. You know, it's like, are we putting a lot of weight on the rear? I feel like we're not. I feel like it's pretty uniform. Oh. Yeah, this walking is a big mess, big mess. So, yeah, so one of my theories is both sides, both legs, if again, if we assume this is a biped, both legs should move at the same time. One should be pushing forward as one strides forward. That way the other leg doesn't act like a pivot point for you to rotate. I think that makes sense. And the other thing we could check is if maybe we can do something about the rear leg. Well, we could check the weight distribution and then see if we can do something about the rear legs angles, so we can avoid these situations where the whole robot is kind of like tipping backwards. Yeah, like this. See, these shouldn't happen. Look at this, like here, shouldn't happen. Feel like that feels wrong to me. So let's do a quick scale test. Let's quickly stand the robot on the ground, put a scale, and see what comes out of it. All right, so there's a robot on the ground. We're gonna make it stand and, oh, wait, no, it's not stand. It's standing now. Here's the scale, and I guess some paper. And what we're gonna do, first of all, we've never weighted the entire robot, so we can try weighting the entire robot. It's just gonna stand on its own. Standing is easy now, right? I mean, once upon a time, standing was exciting. We made a video, oh, it stands. Now we can just stand any day. That's progress right there. All right. So the entire robot. Oh shit. Seems to wait. Oh, actually, I can put it like this. All right, so the entire robot weighs 1,908 grams, roughly. There's some cable there, stuff that's not the robot. And you see, when it stands, front left has 449 grams. Front right has 496, 480, 400, 500, 501 grams, so more grams. Rear right, uh, 859 grams, and rear left has 819 grams. So what we've learned from these is that, first of all, yes, it is rear heavy, which is what we expected from watching the video and just seeing how the robot behaves. And we appear to be right heavy, so there's more weight on the right side. Now that's odd because the battery is on the left side. So I kind of suspect this might be coming down to trim and the robot is like tilted. Now if I see it by the naked eye, yes, the robot appears so tilted. Appears like the right legs are a little lower, so the whole robot is tilted this way. And it also appears that there's a negative brake, so the robot is kind of like the front is higher. So these are things that we can fix with code. The thing is, we don't have a IMU on board, so an accelerometer. So we don't know what flat looks like, other than like if we were to eye it up. So maybe something that would be useful would be to put an IMU on board so the robot knows how much it needs to trim the legs in order to achieve flatness. So that could be an interesting idea. So I'm gonna write IMU question mark, and yes. Now, of course, we could sit here and kind of try to trim it and get these weights stable. That's one way of doing it. We could also try to find an IMU. I think a lot of phones have like a level that we could put and use for that. Now, I don't know how big of a deal these off balances are, or if I'm just using this as an excuse to justify that, to say like, oh, my walking doesn't suck, it's like something else that's wrong. I kind of think that if the walking sequence was better, that this wouldn't be an issue.
Also, there's a lot of play on the robot knees. That knee joint, that 3D printed joint, has a lot of play. So we need to tighten that. This is unacceptable. Look how much it shakes. And that only happens in that axis. Like this way, no shake whatsoever. Yeah. The shoulders are, very stiff, but the knees, oh man, they're all over. Look at all these. That's just from the knees. That's really not good. Maybe we have to put the screw back. But anyways, let's try to work on some things we've discovered so far. Let's write some code that's improved walking sequence, and let's start from there.
By the way, just wanted to a quick vibe check on the project so far. We're approaching the point where I'm like doubting, like, oh, why am I doing this again? It's really hard, It's really hard. Yeah. So let's take some notes. Let's document here the findings that just happened, right? So, weight distribution. Right, so total mass, okay, we're not gonna talk about the difference between weight and mass here, right? This is technically mass, it's not weight. Total mass is 1.9 kilograms. I like metric. 1.9 kilograms per pounds. 4.2 pounds. It's like 420, basically. By the way, I have Apple Intelligence now, so now you can ask, what is 1.29k in pounds to Siri, and it should be able to do it. Boom, close to 420. From left, from right, rear right. I put rear left here, so we know left and right. These are kind of like approximate, of course, but. And if you're wondering why the totals don't add up to our total mass, it's because that makes sense. I think to get a clean weight distribution, you have to measure like on an even surface, maybe all legs at the same time. That's not what we did here, but this is an approximation. You can tell that the rear numbers are 800s, the front numbers are mid 400s, 500s. So obviously it's rear heavy. Robot seems to be rear heavy as suspected by watching the replay videos of it trying to walk. Robot seems to have a negative rake. So rake, if you don't know what rake is, a rake it's an automotive term. Apparently I'm making it up. The setup out of rakes. Maybe it's like a very niche Formula 1 thing actually. A 1.29 degree rake, right? It means there's this is slope here between the ground and the car ground, the floor. So 1.9 degree rake, any positive rake means that the rear is higher than the front. So we have a negative rake in this case where the front is higher than the rear. The front is higher than the rear. Both of the observations above are obvious to the naked eye. Perhaps we should add an IMU so that the robot can trim itself and be flat. Perhaps. For now, it seems like perhaps not. All right, let's see. What else do we have? So this is our code. This is a standing code I just pushed. This is a walking code. This is what we used last time to try to walk. We can we can run it. Let me see. I have the following code. I'm gonna ask the AI. I have the following code. How can I stop it through a command? So I think we can. I think for Arduino, there's this thing called the serial monitor, and we can send messages. So through a message on the serial monitor. So you can send messages to it. I think that's how it works. I'm thinking like, oh, Python script, you know, you can interact with it through writing on the terminal. Maybe it's the same thing. Okay, so if we send stop, it was hard stop. We'll see about that, but okay, let's see. All right. So we are initializing the serial monitor this time around at 19600. It should be fine because none of the pins we're using are in pin 0 or 1, else it would be conflicting. So I'm gonna push this code and we're gonna see what happens. We should see movement. It should walk. I swear it looks so clean. It looks like it should walk, right? I'm just watching it walk. But yeah, it's actually, like, now that I think about it, it's actually kinda, you know, a little silly to expect it to go forward when two of the legs are solidly planted on the ground, right? So two legs should be pushing forward while the two others are on the air, so there's no resistance, right? That's what makes sense to me right now. I think that's what we're gonna do first. All right, the other thing is, like, since we added that code with AI, I should be able to write stop here and it should stop. All right, what if I say go? Okay, so stop, it won't continue. Okay, I'm gonna say thank you, but now I need a command for it to continue if I indicate it to continue on the serial monitor after stopping. You know, pretty straightforward. Let's see what comes with. And this is really just Code 3.5 Sonet doing all the coding here. I'm not that familiar with Arduino. I'm learning right now with you. You know, I'm relying very heavy on the AI to code a lot of this stuff. So let's see, let's try that. Let's upload that. We're really just testing the stop and continue. Stop and go. Stop and go. All right. So stop. Fast. That almost felt like a voice command. Go. Cool. So we can now stop it and go. Cool. All right. Coke Zero Cherry, by the way. It's one of the advantages of living in the US. We didn't have this in Canada. All right. Man, so annoying. I can't use my mouse while I have the Arduino connected because my Mac doesn't have enough ports. So I have to use the trackpad. All right. I have the following. I'm gonna keep talking to the AI. I have the following code to help walk my quadruped robot. I've noticed that the walking strategy is wrong. We are attempting to walk by moving the diagonal legs forward while the two other legs remain stationary. This leads to the robot to rotate side by side. Instead, we should push forward with a pair of diagonal legs, and the other diagonal pair of legs should be on the air moving forward, striding forward. In general, the angles, the servo angles for all faces 1 to 4 are correct, so we can continue to use them. Let's see what it comes up with that. And feels very awkward narrating what I write to the AI. Maybe I should just switch to voice commands. Okay, let me help you optimize the focus. Okay. By the way, like this AI thinks it's Patrick Bateman from American Psycho, and that's why it says it's talking about its morning routine. That's why. And you can change that. You can change that here on this tool. Here. This is, yeah. Just a personal preference. I'm going to click here on the thunders to implement the code. Let's see what it does. I want to save this as walk-in b0 just for memory time sake. And I know, GitHub keeps a rev and all that, but we're never going to see that. So I'm going to implement this again. Okay, so what is zip right A? It's complicating things. Okay. Honestly, it's complicating the code a little too much here. Do we still? Yes, we do. Okay. Let's just run it. Let's just run it. Or I'm a visual learner. Oh. Some of these angles look really, really bad. I'm rolling back the code to the previous one. So now we have to take a closer look at what the AI is trying to do. Obviously it has messed up some of the angles. I think I know what's wrong. So you cannot use the same angle and expect the same output on all servos. The left servos are mirrored with respect to the right servos. An angle of 0 for the hip servos on the right is equivalent to an angle of 180 for the servos on the left. The range for all servos is 0 to 180. An angle of 90 for the servo's knee on the right is the same as the servo knee on the left, but 100 on the right is equivalent to 80 on the left. 0 on the right is equivalent to 180 on the left, flat. Let's try that. So I think it's just, it didn't understand our setting here. which could be very dangerous because we could have damaged the servos. I suspect we didn't, but man, this code is getting complicated. Maybe for no reason. Okay, so we have there's phase 2. There's no phase 3 or phase 4. So it appears like there's a phase 1 and a phase 2. I'm gonna entertain it for now. And I just wanna see if it got the right idea. Did you get the right idea? I mean, it works now. I suspect this is not gonna work. It's too slow. It's like the legs that are in the air for a long time, whereas they should only be on the air for the final stride. So this is, I'm gonna be encouraging. This is much better, but the legs that are on the air for much too long, which causes the robot to be unstable and might fall over. The diagonal set on the air should only be on the air for the final stride where the other set of legs push forward. Does that make sense? Let's see. It's the power of AI. Now that I spend less time in the air. Oh, it's making jokes there. AI humor. Here we go. This first line you can ignore at CPP. It's likely an LLM bug. Okay, well, I mean, okay, it's decreasing one of the delays, which I guess it added it here. It's decrease it here. Wait. Okay. It didn't have to change the formatting here, but it just basically, instead of doing math, it just jumped to the constant answer, which is fine. But if these were not to be constants, maybe it won't be fine. But I don't even know if you caught that. But all right, let's see. No, it's still not doing it. Still not doing it right. That's something right. What are you gonna drink? so if you take a closer look, let me just tell it to go again. The leg is still spending too much time on the air. Pretty sure. I think so. At least I think so. Yeah, I think so. It's like it's not going back to the standing position. Yeah. Okay, so I'm gonna be very. I like to be encouraging to the AI. You know, it's like close, but not quite. The diagonal set that is on the air should be on the standing position for the most part. It should only go on the air when right hip, right knee. I don't know if it will understand. I don't think I'm being very clear, to be honest. We'll see. Let's see. I think this is correct. Alright, see, I see the issue. It says, I think it thinks that when I say on in the air, it's the it thinks it's the legs that are moving, striding forward, and I meant the other two. Thank you, but not quite. I think the legs that are meant to go to the standing position is actually the other set of legs. So let's see if that works. We're getting close. This is kind of like the back and forth of what coding with AI looks like. So let me implement these. Let's see what the changes are. First person. Okay. Well, let's see. It basically just flipped the angle. So let's see. I'm also gonna upload this to GitHub just so we have some revision history, which you would still have anyways. But all right, let's see. Nope. Nope, nope, nope. I'm gonna ask you to add comments. Can you please add comments specifying how you are naming the different legs? What is a support pair? Okay. Some comments never hurt. Okay. All right. That diagonal pair currently pushing against the ground in contact is the active pair. The diagonal pair that's maintaining a default standing position until it needs to quickly lift and stride forward is the standing pair. That I guess that's correct actually. I could did AI just convince myself? But I think that's correct. Something went terribly wrong there. Rolling back to code. I am trying to understand if it's wrong. I'm just like trying to picture how walking would go. I don't think this is working. This isn't working. Let me try to. Let me see. Boston Dynamics quadruped. Let me see how a different quadruped walks. See if I can clean my palette here. Or we're gonna get copyrighted. So look how the legs are kind of like angled inwards. Oh, just flexing going backwards. Okay. So. Well, okay, that's exactly what I was describing. That's hardware, that's very nice hardware. Man, I have so much work to do. um, okay. Actually, very nice how it stands up there. But okay, let's see. Can I do a slow motion? All right, one foot going up. God, so smooth. Going forward. Man, it's so elegant. We're in trouble here. We need to catch up. The leg doing the walk and like moving up, it's very obvious what it's doing. It's just what is the other one doing? I can see it flexing and stuff. I can see it moving. I guess it's solidly planted and it's just reaching. And then the next one's reaching. And then the next one's reaching. That also makes sense. It's not doing these acrobatics where like one pushes and the other one's in the air. It's just very solidly planted. 1, 2. Does that make sense? It does make sense. But it's not as simple as that because I mean, even as it does that, the other leg still has some movement to do. Okay. Give me another drink. Very clearly above my pay grade here. What about a G1 robot walking? Unitree dog walking. Okay, I would say not as clean. Oh man, they already did the treadmill thing. I thought I was gonna get some clicks for that, but no. It feels like it's taking smaller steps. Can't play back very slow here, but. Playback speed, super slow. Look at the one at the left. feet planted, other forward. Let's take a look at what we have again. Yeah, that's not it. I'm gonna flash blank for a bit here. And okay, so okay, I'm gonna power off then. Okay, so if our standing is somewhere there, right? Then I want to lift, put it here. No. From here, lift, move here. And now this leg is here, so we kind of move forward. And then next, this is gonna lift and do here. Wait, does that make sense? No. 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 Why is this breaking my brain? Okay. So floor, up, this is really breaking my head. My brain is gonna explode. It's like here, and it's like as you go up here, you're here, and then you push back. And this is as you're pushing back, really. Now the other leg is doing the here. So as you push back, so I'm basically go here, I'm pushing back, and then the other leg is here. It's pushing back. Now, kind of like that. Okay. I think maybe I got it. Let's Google something. How to walk a quadruped. What is this? Competitive female training? I'm sorry, what's going on here? What is this? Oh. Okay. It's just the name is kind of sus. Let's see. Why are people recording themselves walking? What's going on here? This is how you learn parkour. Oh my god. Is that how it works? Programming. There's already a tutorial to do what I've been trying to do for weeks. Not quite, not quite. Anyway, should have done inverse kinematics. This is cool, but it's not the same design actually. This is kind of like a crab, not a dog. I guess the thing I'm struggling with is I understand how to move the leg forward, but I don't understand is once you move it forward, how do you tell it to kind of keep pushing? It's a very subtle movement apparently. Maybe we can just first code the moving forward part. So let me see what code we already have. This is where I'm glad we saved our original code here, because I think that's a better building ground. All right, so let's take a look what we have. What would these used to be? Oh, everything's off. Totally forgot. I don't think this is too far from where we want to be, right? It's just our timing is off. Maybe I should build a library of slow motion videos to learn. Yeah, because right now it steps forward. Right now we step forward and immediately go back. This one doesn't really do that. Steps forward and then slowly goes back as the other leg comes forward. Okay, let's try talking to the AI. I usually start with these. Explain to me how this code works. And I know we're not making a lot of progress here. I know I'm just literally at my limit here. Never done this before. This code works in a 4-legged road with 12 servos, 3 per leg, shoulder hip. The walking gait is like a high-end trotting pattern where the diagonal legs move together. Okay, the move legs function exceed 4 phase movement sequences. Lift, plant. Okay, so lift leg. Yeah, so we have a 4-step. Okay, so I see the lift. Plant forward. Can you tell me what happens on each phase of the walk? Okay. I'm not quite getting it, so I'm gonna do it this way. I'm gonna comment out the code. I'm gonna see face by face. Okay, I see. So that phase, so I'm gonna write my own comments. In this phase, the leg strides forward. Okay, cool. Next one. Okay. In this phase, the leg pushes all the way back. That's from what I can tell. In this phase, the leg raises up in the air for clearance. Okay, and this is just standing. In this phase, the leg is in the standing position. I messed up the formatting a little bit here. I'm gonna go for another drink. I'll be back. now that we know what each face is, let's figure out which faces we're missing. Alright, so this one here is on the standing position. This one here is pushed all the way backwards. This one now, this is on our face 1. In this face, the leg strides forward. So okay, so basically, okay, so the left goes from face 1, right, forward, planted, standing, right, never actually pushes all the way back. There is no equivalent to pushing back. It's like face 1, face 4. Standing. Up. Oh. Alright. Going forward, face 1. Standing. Air. Which face is air? Air is face 3, and then repeats to face 1. So we don't need the phase 2 of pushing backwards. Now let's take a look at what happens on the other leg while this happens. So we said, okay, so left leg is doing phase 1. During phase 1, the other leg is at phase 4, standing. Now that this is at standing, the other leg is at phase 3 and goes to phase 1. Wait. Standing, air, stride, standing. So it's like stride. So stride, I'm just calling like stretching forward. Phase 4 is standing. So stride, stand, air. And it's like stand, air, stride. So is it fair to say that while the left leg is standing, the right was going towards the air? Standing, air, yes, stride. Okay, I see. Now, what is one thing to note here? I don't know what's one thing to note here. Why is it not pushing backwards? It doesn't need to. It doesn't need to. Bit confused, but let's try this. I have the following code to walk my quadruped. Whoa. I'm gonna add a comment here. How can I add? I don't know how to add long comments. gonna say what I said. I'm gonna say this. I'm just gonna add this for the AI mostly, so I'm gonna comment this out. I have the following code to walk my quadruped. I think the walking motion can be done without phase 2. Plan forward. I want to try removing this phase, and instead we would adopt the following sequence. Left, first diagonal set of legs would go phase 1 to phase 4 to phase 3, then back to phase 1, and the cycle repeats. While this first set of legs is on phase 1, the other set should be on phase 4 when the main set of legs is on phase 4, the other set should be on phase 3, and when the main set is on phase 3, the other should be on phase 1. I think that makes sense. Let's try it. Like, it doesn't make sense to me necessarily, but like, that's not how I would have thought about it. But that's what I'm seeing on the videos. Alright, so up, stand. Okay, well, this will 100% not work. There's... Oh, the camera isn't working. Alright, this will 100% not work. Sorry, I thought the camera was working. This will 100% not work. As it's like both legs are in the air simultaneously. Which I don't understand. So it's 1, 4, 3, left hand side, 4. Yeah, I don't think this is how Boston Dynamics is doing it, right? First of all, leg is always on the ground. What we have here is we have times where both legs are on the air. I'm just taking notes of what I'm seeing, so I'm gonna call it out as I see it. So left just took a stride, and the right is going up in the air. Now the left is standing. Air, standing, stride. I don't know, did we have the right idea? It's just, I think that it needs to be like out of, like we need to, right now they're on pair, we need to like shift them out. So I think this is the right idea, but right now we have both diagonal sets moving in pair. I want to introduce a phase shift between them, measured in some sort of time constant. Let's see what it proposes. Let's introduce the sigma phase shift with a clean delay. Oh, look, it's using emojis now. Okay. Let me see what this looks like. Honestly, I didn't even feel that delay. Let's try half a second, 500 milliseconds. I see what it's doing. So the phase delay should not delay the complete stride. It should just change the sync between the two set of legs. But the overall time to take time or pace of walking should not be affected. How can we do this, right? So our implementation add delays, which also makes it walk in slow motion, which is not what we want to do. We want to change the movement respect to each other if we think of left and right as different cycles. explain. Time for each phase. What is phase time? I'm not sure what it's doing here. Let's just try it, because but I think it's overcomplicating things. Something broke. It's not working. Alright. Basically going in circles. Let's do on circles. I think we're getting worse. Okay, so this is code to control a quadruped robot. I'm just adding some comments here for the AI instead of, so I don't have to type the same thing over and over. Are you familiar with the Boston Dynamics spot walking gait? Would you say this is similar to it? Okay, I see. Even the AI thinks our code sucks. Why is walking so hard? Honestly, I think this original code, it wasn't that bad. We just need to fix the issue of like one side being completely static while the other one attempts to walk. gonna add back my commentary. And then I'm gonna save these as the original walking motion, so we have that. It's like a save, like a checkpoint. And now I think this is fine. So I have the following code. It works okay for the most part, but I think we can make walking much smoother by fixing the following. Right now, one diagonal set of legs is in motion while the other one is completely static. The static pair of feet drag on the floor, not allowing us to move forward in a straight line. To fix this, we should make sure that as the moving set of legs enters phase 2, the static set of legs goes into phase 3 to create clearance to the ground. After phase 3, the static set of legs would go into phase 1 as the moving set of legs and go into phase 4 and take this static role. That makes sense to me. That makes a lot of sense to me. I just like I don't know if the AI is gonna interpret correctly. The time is crucial. Oh, this is a new walk cycle. Oh man, okay, we're gonna blindly trust this. Okay. The legs are clashing, which is funny. I don't know. Maybe work. It's going backwards. It's going. I don't know what's happening here. I want to go straight to the ground. That's what's happening here. Actually, Let's try something different. Let's try a better AI. When in doubt, let's use O1. O1 is the most capable AI supposedly, so it takes longer because it thinks big brain, but let's see. And I guess if the AI can't do it, I'll just code it manually. Wow, this is a much better. This sounds much better so far. Define faces for each diagonal per front, left, and diagonal 1, diagonal 2. State machine for each diagonal. Each diagonal will process through its own set of faces independently. Yes. Remove blocking delays. Use millies to handle timing, allowing both diagonals to update their states without waiting. Modified code. I mean, I'm excited to try it, but see, that's the thing with O1. It always removes the comments. Man, it messed up the angles. Rookie hour, rookie mistake. Introduce an enum face to define for each diagonal pairs. I'm gonna remind it of the angles because it messed them up, and it's gonna take a little bit to get back to us. Let's see if it can fix it. And if not, I'm just gonna code manually. This AI thing's not doing it, man. I guess I should have fixed it this time around because, you know, it's the most capable AI. Nope. I'm gonna give it one more try. The angles are still messed up. Refer to my original code for angles that work. Let's see. We might be asking for too much here. How to walk a quadruped robot. Basics. Oh. No, we're doing trot. Man, this picture's not helping me. Static stable gait balance of forces maintain inertia force. Yeah, I agree. Very nice. Oh yeah. Oh, I see. We should be able to do a crawl. Basically, only one leg goes up at a time. And then, yeah. Trotting and stable. We're trotting right now. We've been trying to trot. It's hard. Okay, one last try before we go full manual here. Before we give up an AI and just say AI doesn't work. Guys, your jobs are safe. AI doesn't work. I'm gonna flash blink. I'm gonna get a drink. We're gonna code these manually. Where's blink? Blink. Actually, blink wouldn't work actually. I just want to make sure all my servos are healthy. Man. No. Looks like blink is on the same one of the same pins as we're using for the servos. Okay, that's standing. We can still stand. Looks like one of the servos disconnected here. The power, yeah, we had lost one servo somehow. Smell test. Things appear to be getting hot. Smells like hot filament. I don't know what's particularly. Not the servos. Servos are warm. The switches are not hot. Okay. We've been running for a bit and nothing's hot or anything. Alright, BRB. Alright. So we're gonna start here from our checkpoint, walking B0. Gonna upload this code. Alright. So what's wrong with this code, right? We're trotting. We want to crawl. How do you crawl? Yeah. So I guess you move one leg forward, then everything touches, and then the next one forward, and then the next one, and the next one. Eventually everything's forward, and then you go back to standing position, right? Does that make sense? I can kind of hard code these. So the way I would hard code this would be in this phase we don't need these. I guess we can use these. Okay, so we rename these phases phase 1, 2, 3. Stride forward. Lift leg. Lift and leg is phase 1. All right, so all right. It's just so dirty to code this way, but okay. So assuming we're gonna do the front right first, okay? So FR hip right, 35. FR knee right, 130. Right. Our front right is is in the air. We're gonna delay by 100 milliseconds, and then we're gonna stride forward. So FR hip right, 90, and then FR knee we're gonna write 150. And so if we run this code, our right knee should go up a little, wait a little bit, and then forward. I made a typo. FR hip, capital, FR knee, capital K, FR hip, capital H, FR knee. I think that was it. C is a case sensitive language. I think our delay might be too short. It's not. It's only doing the first position. It's only lifting it up. It's not going forward. And I know you can't see. So now you'll be able to see. So you see how it's up. FR knee, FR hip, right. I think we need to add another delay here for this to work. If I remember how Arduino works. I'm gonna move you to my side so we can both see it at the same time. Oh. There are so many wires. Right? Okay, longer delay, not enough. Okay, cool. I mean, that seems simple, but that's exactly what we wanted to do, right? So, and then sorry. Oh my god. My void loop is not respecting the stop command. How can I fix this? I modified the code and now the stop command doesn't work. So I'm just gonna ask the AI to fix it real quick. Oh, I guess O1, that's a mistake. Okay, let's see. Just some very simple code here. Alright, so I upload that, should work. Cool. Say stop, should stop. Alright, cool. Okay. All right, so FR step forward, front right step forward. Now I guess RL step forward, rear left, and I'm just gonna reference to my code here using the AI thing as a notepad. So RL hip, of course, that's on the left side. So 145. I'm just looking here what it was before, because before we've already figured out what the right positions for a left hip, a left knee, a right hip, a right knee, to lift in the air, to go forward, and so on. So something like that, something like that, something hip, right 90. I am very Are you sure, man? Yeah, actually that makes sense. That makes sense. Okay. So as usual, we write some code, we run some code. So now I'm gonna add a super long delay here so it just doesn't loop like that, because we don't want it to loop. Yeah. Now, what would be a more stable crawling technique, right? Here in their example, they did rear left first, then front left, and then to the right, right? So they went left to right. Is that a more stable one? So maybe we add the rear here. The good news is that it's super easy to change. So, I guess this more stable. We could probably even try it. I think my last concern is maybe our ground clearance step when we lift the leg is too dramatic, and it's gonna be unstable, and it doesn't need to be that dramatic. Anyways. See, in this position here, I think, because we're so back heavy, I think we would just fall backwards. Oh, of course, the last command here is everyone stands up, right? So everyone goes to stand, and in theory, we've moved forward. This is all very theoretical. Yeah, so we can try that. Okay. And now we can minimize this delay. And this is kind of like basically a crawling sequence. Really on 4. It's crawling, right? Stable as it gets. So I want to increase some of these delays. Which delay are you gonna increase? I guess it's like, oh, I guess we don't have a delay here. So I'm gonna add a delay here at the end, because right now, as soon as we are putting our foot for taking the step forward, the other foot is going up. Looks a little unstable. See, now we always have 3 foot on the ground. Yeah, I think now what we need to tune is the angles of the legs. The rear feels very unstable, especially there. That's not stable. So even if we take smaller steps, in order just to get more stable for the crawl, that's fine. If you're thinking this guy's drinking his entire fish, you're not wrong. But soft drinks were like 60% off this weekend, so I stocked up. Okay, so wait. I can't see. Oh, where are we falling? Okay, so the first thing is we're gonna bend the knees a little bit more on the standing position. We're also gonna simplify this code. We don't need this anymore. Okay, and so if we comment this out, it should initialize at standing position, I think, based on these. Yeah, okay, so that's standing. And we say, we basically want the rear hip actuator to be a bit more horizontal, to make the rear of the robot more stable, I think. And so, you know, if we're at 70, we can try 50. And for the other one, you know, we basically at 20 degrees, so 130. So we can try that. Right, so that looks more stable. The other thing we could do is to run a positive rake angle, right? So now the rear hips would be, for example, 40 and 140, and the front stays the same, right? And if we have that, then our standing position would feel something like that. Actually, that looks terrible. That looks really bad. That looks like it wants to jump. Might have overdone it there. I think I can change these live. So I can move these to 40 and these to 130. And it should just lift up. Only once I did it. It's kind of weird. I don't know why. Rear right at 40. Yeah, what the hell? In general, the right hips seem to be well. So maybe this is where we add some trim components to it, but it's just gonna be eyed out. So let me ask the AI to add some trim components. So I'm gonna say I have the following code. Sometimes some servos are slightly off, due to how they are installed. I want to add a trim constant specific for each servo so that the final angle is adjusted according to the trim constant. Final reading. What is the most convenient way of doing this? Right, so we can try that and see what it comes up with. Let's see if it can implement this. I mean, that's one way of doing it. Honestly, a little dirty, I would say, but so okay. So now we can try adjusting the trim. So the rear right hip needs some positive trim. Let's try 10 degrees. Oh wait, actually, thought I forgot to comment some stuff up. Forgot to comment the walking sequence. I need to comment this out. Okay, now should go back to standing on our lower crawl. Yeah, and we added some trim to the rear right. We're gonna add a little more trim. Let's see what happens. Maybe it should be a negative trim. Yeah, that feels much better. And then the front right hip, also trim it by 20 perhaps. Since this guy's flying right now. 20 is probably too much for the front right, so we're gonna do 10. Can't see it. Alright, so the robot's now more stable and it should to your naked eye, kinda hard to tell from that angle, but it should look flattish. Okay, so now we have that. I guess now we can try walking again. So I'm gonna ask the AI one more thing here. On the void loop, when under the comment, the angles should be the same as in as those under. Can we make sure the void loop pulls from the standing position defined above? I'm basically trying to not have to define the standing angles twice, mostly for consistency and for so the code is good. Else, I can accidentally, maybe I can forget to adjust one standing angle and so on. Okay, yeah, again, that's one way of doing it. This code is getting a little dirty, but it will work. It's just it's more painful to work on it. Now I'm just gonna verify these with the crawling commented out. just to make sure everything works. And now we're gonna attempt to crawl again, this time on our box. Let's see what that looks like. Alright, so since we adjusted the standing motion to be a little higher, now when our legs are going quote unquote up to clear ground clearance, they're not actually going up whatsoever because our standing is already kind of like more tilted up. So we need to adjust that. And also I think our stride is too long right now because the rear legs look very unstable when we go forward. So we'll just continue to fix those things. So we could just do trial and error. Basically, if before we're doing 40, well, okay, actually our standing position, you see, one way of doing this would be to define the clearance based off the standing position. So it's standing position minus something. So for example, standing, I don't know what right hip, the Arduino IDE doesn't call constants like that. Let me go to VS Code. Okay, so here I should be able to do standing right, well, all caps actually, standing right hip minus, stand right hip. What is stand right hip? Stand right hip is 40, so minus 10, and then stand right knee minus, so stand right knee is 130 minus 10. So we can see what that looks like, and this is on the front right. Oh, we made a typo, I think. I think we can't do math, I think. X is the name. Did you mean XH? Or is there an X? Servo X. Oh, I accidentally added an X here. Alright, let's try it. Should be a plus. I'm gonna make it more dramatic because I didn't see anything. That was very dramatic. Alright, going down to 15s. So basically 10 can't see anything, 20 is too dramatic. Okay, I think that's good. And then we do the same for this guy here. course, we're gonna fix the final like the stride forward after. It's super unstable right now, but now we have to do this for the left side, right? So I think for the left, standing left, the standing constant is different. And I think this would be a plus, not a minus. And standing left knee, and this would be a minus, not a plus, something like that. And this is rear left. Looks decent. Oh, okay. So now we propagate to the last servo here. And now we have to fix the final stride. I still think maybe it's too dramatic. The 15s are going down to 10s. It's a crawl, right? It should be a very chill crawl. It's not like we're walking over obstacles at this point. We just want to crawl across a living room. Alright, I'm gonna tell this to stop here. And now let's do the forward stride. Forward stride. So FR hip. I'm gonna comment everything else because we don't need it for now. And let's loop this. Let's get the loop going. All right. So those are our 3 key positions here for the crawl, right? We have standing, clearance, and stride. And so stride is too much. So we can. I'm just eyeing it out really. Let's see. That kind of made it worse, I think. I want to pull my safety matrix here that tells us, that tells us what angles we can go at. So at 170 we can go up to 160. So we have some room to spare here. Let's try 150. Really, I just want that foot to go forward. Right now it's going kind of like forward and down. 160. And this is where having reverse kinematics would help, I think. I think that looks much better. Now you can imagine if this was the rear leg, would that look also much better? I'm gonna add the full right side. Let's see the rear. Still feels a little unstable. Can I get a drink? I'll be back. Let's take another look. Yeah, it's very unstable in the rear. Is it because of the trim? It's possible that's because of the trim. But the trim looks good on the standing position, so. Also, what was this before changing? Oh, I guess 150. $90 and 150. So 110 and 20. I'm gonna remove the trim here, see what happens. I mean, it looks better. It's like the way it behaves under load is different. Yeah, these really don't. It's like they don't. Let me try on a different surface. It's kind of moving forward, but all right. So one other observation is that the robot is not stable on 3 legs. So that step where we raise one leg to create clearance to the ground, it actually, the entire thing comes down. So one thing we could try to do is like just do that step faster, so there's no basically no time for it to come down. I don't think that's gonna fix it, but we can try it. It's easy to try. So let's see, where is this? Right, so we're waiting half a second here basically, and so we can just wait. We kind of need to 100 milliseconds. We kind of need to see how long it takes for the servo to move. See, now that sounds way more organic. Now the other thing, I think the knees, the lower leg angle, when it gets too horizontal, that basically puts our servo in a pretty bad position. So the legs might as well, the knees might as well be completely horizontal, right, at this point. So overall, we want to increase that knee angle. It's not doing us any favors. Even on the standing position. So let's repeat this exercise. So all we do is stand, and let's see what those angles look like right now. All right, so those are our standing angles. So I'm gonna bring the hips, sorry, the knees a little more vertical. I did the opposite there. So 40, 130, 90 plus 50. Okay, so I think it's pretty horizontal, right? So now if we were to put these on the ground, and maybe you can't see. I mean, it's like super slanted one way. Like you can see from this side. You see how it's slanted one way. So I want to bring the trims back. Right, so that fixes that. So with these trims, so now it's flat, right? So that's good. Flat on standing. So these are standing trims basically. You know what? We could even make it more horizontal, I think. Oh, camera is way off. Yeah. Even what about more? What about more horizontal? All right, that's very horizontal. Okay, so the beeping is from the battery being low, so I'm gonna recharge that, and then we'll continue. Alright, so it's this voltage monitor that beeps when the voltage of a cell drops below, I think 3.8 volts. Should be 3.6, but it might be very conservative. So they're at 2.54 right now. 2.569, 3.58, 3.54, 3.53, 3.45. So our pack is very unbalanced right now, which is odd. Two of the cells have way lower voltage, which is super not ideal. Especially because they dip below 2.8 volts, which is usually the minimum you want to go for lipos. And the issue is when this happens is that usually the chargers do not want to balance the cells, right? So this is the charger I use for these cells. This is just from Amazon. It's a pretty standard charger. And you grab your pack, you turn this on, and you connect it. They have XT60 and a bunch of other connectors. And then you also grab this other white connector. And this is the balancing charger. So it wires independently to every single cell in your pack. And so every single cell can also be charged independently. And so you can balance them. You want all your cells in your pack to roughly have the same voltage. This is a 6S, which means there's 6 cells in series. All 6 cells in series should have roughly the same voltage. Now the way these chargers work is you have to select the battery chemistry. In this case, you have lithium, which is what this is, a LiPo, a lithium polymer. But there's other options like nickel MH and lead battery and kind of like custom things. If you select lithium here, you can tell like how much current to load at. Loading current is usually a function of the cell capacity. So if you really want to charge fast, you can look up the charge rates. That's usually called 1C, 2C, as in like 1C equals the capacity. So as in like this is basically a 1 amp hour cell, so you can charge at 1 amp per hour kind of thing. So I'm charging at 2 amps here. Should be fine. And so I'll just click start. It's gonna check that the cells are balanced. In this case, it's so unbalanced that, oh, actually it didn't complain. Usually it complains. It didn't complain. So now it's charging, and it's pretty straightforward. You can get one of these from Amazon for like $20 or $40. And I usually keep, in this case, we have 3 different battery packs, so we're never out of battery. All right, let's go back to this. So, just turning everything back on. All right, so this is our new standing motion. It's it looks much different. But I think this is what it takes to have a stable robot, basically. Our trims are also a little off right now. The right side seems to get in a lot more of the load, so we can relax those trims a little bit. The trims might not be linear now that I think about it. We try to get an even weight distribution between all legs. It's not always perfect, but I think that's pretty good. All right. So from this new stance, now we go through the same exercise of tuning the other 2 steps of the crawl. At least now we know we're going for a crawl. Right, so that's what we have. And let's uncomment some of this code. We'll do, where's the camera? Front right? Yeah, we'll do front right first. So this is what we have so far. Feels like, well, it just feels very exaggerated because those 10 degrees are doing a lot of lifting. And again, I think all of these just points that we just need to do the reverse kinematics for these legs already. FR hip for knee. Yeah. So I'm gonna base this forward stride also on the standing position. Actually, yeah, probably not. It's just going too far up. And that basically means we're flexing the hip too much. So now if we look at our safety matrix here for 60, yeah, 60 should be fine. And so that got worse. It looks like it got worse, but it's because now we need to bring this knee down. And really all we need is like a very small step forward. I mean, that's small. What about even smaller? I think that's good. I think that's good. And now let's see how that looks in the rear right. Oh, actually, forgot about these. I can try it. I'm tempted to make the steps even smaller, but you know, I feel like we can't go too small in the beginning. That's not a thing. Just gotta play it super safe. Okay, what were these angles before? Front right. So the right went from 90, 150. So this was 90 and this was 150. So minus 30, so plus 30. And then minus 10, so minus 20, so plus 20. I think basically this. Now we're doing a strategy where first the right legs take a small leap and then the left, and then everything comes forward. We could also do front and then rear and then everything forward, or rear and then front and then everything forward. The only one I don't think makes sense is diagonally. But let me see if this actually crawls. Remember how I said like, oh, I want even smaller steps? Let's do it. Smaller steps. No, even smaller. Yeah. I don't know why it's going backwards. Let's increase the traction to it forward. Okay, so we're doing even smaller steps. Oh wait. Maybe I messed something up. let's do some math. So 110 no, okay, so 60 on the hip, it would be 120, and 120 on the knee would be 70. So maybe that's why we can't walk. Yes, that looks much more symmetric. Oh god, fingers crossed. When we launch forward, much people were forward. We're not really moving. Like, it's moving the legs, man. It's not moving forward. It's going backwards. Okay, it's possible that I exaggerated and made the steps even like too small. That's entirely possible. I think if this doesn't work, I'm just gonna go read a little bit more on how this actually is done, and take it from there. 20, 60, 60. Can I read some of these days here? It's very interesting how the sounds of the robot change. Oh, somersault. That's easier than walking. Alright, so it is possible that I've exaggerated the stance. And I've gone too far the other way, or unstable the other way. Okay, one more try. Alright guys, one more try. Stuff goes like, it actually looks pretty good there, you know. All right, standing right hip. Okay, wait, unfortunately need to make the hips a little more vertical. I think. And then the hips a little more horizontal. Sorry, the knees a little more horizontal. A little more horizontal. Maybe. Okay, cool. Okay, now one test I want to do. Just want to see if what happens if right, so if the I don't know, can can we stand on 3 legs? No. And it's not even close, guys. Alright. So this might sound desperate, but I have an idea. We can't stand on 3 legs right now. But what if we flare out the shoulders a little bit? That would help, right? That would help. See, N equals L. We're increasing ln. Yeah, so we could flare out the shoulders a little bit like these, like so. This is probably too much. Oh no. Front left shoulders to the right thing. Rear right shoulders to the right thing. All right. Something like this. Right. So. Actually, I messed it up. Takes so long to initialize. Alright, something like that. Alright, so Okay, now we're very okay, this is an exaggeration. Something like that. Still on 3 legs? No. Alright, maybe the previous thing was not an exaggeration. Let's see what it would take to be still on 3 legs. Let's see if this is still on 3 legs. Also not still on 3 legs. Man, getting my ass kicked here. I'm gonna grab another drink. Which is what we do when things don't work. I'll be back. So I have an idea for how to make the robot stable on 3 legs, which in theory I think will also make crawling more stable, because crawling depends on the robot being stable on 3 legs in order to work. If you don't have that, you really can't crawl, not in a control manner. So right now, we have the front right leg slightly elevated, and if we put the robot like this, it will fall. Where do you think it will fall? To the front right, obviously. Now that means that the center of gravity is somewhere like on this side. Now what can we do to improve that? When we lift a leg on the left side, we could rotate the entire robot slightly to the right side in order to help stabilize it. So that's what I want to try next. So let me try that right now. Actually, it's like super simple. It's not that many lines of code to prove the concept. And then if we like it and it works, it will be a few more lines of code to actually deploy something that actually works. One of the issues of working with 2 IDs at the same time is that it's hard to remember which one has the actual code you want. All right, so here, this is test code, right? This is where we're testing this delete test code, all right? So just like we did that, we could also do, so that's front right, so we could do front left hip and rear left hip. And we could increase, actually decrease this a little bit more. I'm just doing random amounts here. We could calculate this, or there's a typo somewhere. Yes, all caps. I feel like that's a charger saying battery has full charge. Yo, I feel like nothing happened if our hip. Did anything happen? Did we upload? So I'm just not paying attention. Oh. Going in the wrong direction. And just like that, we are now standing on 3 legs. Just gonna move the camera. 3 legs. See the air underneath? 3 legs. And so you can imagine we can do this for both sides. Every time one side is taking a step, it wouldn't be a big deal. And so why don't we code that and we try to walk this way. I think, you know, I can kind of like, I'm just gonna hard code these. There's definitely a more parametric way of coding these, but you know, if I had just to hard code these, kind of like, so. All right, so hard coding these. Let me see what these used to look like. It's been a while. I kind of already forgot. I see. So I guess that's one of the advantages of doing left side first and right side. So it's like tilting body to the left, since we're doing right side first. I don't even know if this is gonna actually, I think in theory these should make a difference, but you know, theory and reality are often very different things. How is that? We're actually moving backwards. It's really funny. Man, yeah. Okay. So that was useless. You know why it's useless though, right? We used the wrong angles. So this shouldn't be this angle for the FR hip. should be yeah, no, that feels wrong. Yeah, okay, that didn't help whatsoever. Let's go back to standing on 3 legs. Okay. So from this position, right, if we wanted the robot to take a step forward, we would just extend the leg, right? Oh, I think continuity camera does this. Did you see that thumbs up? Yeah, so from this position, cool, extend leg. It's like I kind of see what's happening here. All right, we're back to hard coding something. We're gonna hard code an idea here. I've been here basically most day. Where's our, okay, here, this is our idea, right? So so this basically rotates the body to the left. Leaves the that rotates the body to the left. Lift the front right leg up. Rotates the body to the left for stability. There's a delay, maybe wait a little bit, and then we want to front right leg take a forward stride. Bad code is how we break our hardware. That hurts. Stop it. At least it was moving. Okay, well. Oh my god. That forward straight is not good. I said it. We're all thinking it. That's more like it. Right, so it's like, this is the first step to crawl, right? We're almost there, so we foot is up there. And now that the foot is up there, it's like, by the way, not the cleanest crawl ever, but all right, now that you put it forward, then you put it down, right? So that's like how the crawl works. Front right leg touches the ground. Now, this is the issue we have since we don't have inverse kinematics. We don't know at what angle it touches the ground. I think that's what inverse kinematics would do. So maybe I just need to spend time doing that. Let me ask ChatGPT. Inverse kinematics. In computer animations robotics, inverse kinematics is the mathematical process of calculating the variable joint parameters needed to place the end of a kinematic chain, such as a robot manipulator, in a given position or orientation relative to the start of a chain. Sounds like it. Sounds like that's what we need. I need to go study. Anyways, front of the touches the ground. We can always like just get lucky, I guess, but 20 or so. Bring the knee down. Oh my god. Did I make a typo? Oh. Oh, the Arduino is not replying. I think it disconnected the Arduino by smashing into it a million times. See, is that working? Yo, is that working? It looks like crawling. Okay, cool. Okay. So we have that, and now, in theory, we do the same for the rear right, so our hips then. Delay 500, right? So we're gonna be standing on 3 legs again. Oh. Oh my god. How do you even do that? No. Relax. acting like this is such a big deal. We had it. We had it. We were already there. Like, why did you? Yeah, see? Why can't we do that? Okay. Tell you what. I know what's going on here. Being in 3 legs is different. Being in 3 legs, when it's one of the rear legs on the air, it's harder, right? It's not. Were we moving too fast then? Oh man. Okay. Well. Too fast? Got unstable? Oh, that sounds so bad. Well, at least we learned how to rotate. Seems easier to go backwards for some reason. Sec, but oh, I see what's wrong. I see what's wrong. Okay. So this, we're kind of like not going anywhere right now. So change of plans. My next approach will be to, I'm gonna go and, oh, okay, tell it to stop. I'm gonna go and fix these knee shakiness here, which I think it might be causing a lot of the issues we're seeing. Just make things way more unstable. And then the next thing is we're probably gonna have to do the inverse kinematics for this. I'm gonna go see if it's worth it and if it would help. But first of all, let's open on shape and fix the legs, because I think that will do a lot for us. So, oh, forgot that when you turn it off, it just crashes into the ground. I thought we were done with CAD, huh? You thought you were done with CAD, huh? Thought so too. All right. First of all, let's see why this sucks so bad. So in terms of clearance, we have a 10 millimeter diameter going into a 10.6 millimeter diameter. Now, it'll be way easier to just 3D print this bottom part. So 10.6, 10, you know, basically 10.6 minus 10.6 divided by 3.3. So we don't need all that clearance. Move face. Man, I already forgot. So we can move these to by 0.54 and like make it very tight, very tight. Obviously, I'm gonna print just one of them first, and then verify, and then print 4 of them. See, I did the math wrong because now we have interference. Go to high school, kids. Sure, go to high school. Don't skip high school. Yeah, 10.4. I mean, that's not tight. I know that would kind of work, but we want it tight. Okay, so now we have that, and then the other thing is this gap here. We have 0.25. Let's make it 0.1. So this phase and this phase can be 0.15. Something like that. Section view. How in the world do we have 10.4, 10.6? Oh my god, they're different? Bro. Alright, forget it. Maybe it's easier to print the other part, so it's okay. That's crazy. How did we mess that up? It's also easier to modify the other part because there's only one version of it versus the other ones. There's 2 versions of it. Anyways, 10.6 and 10.4, right? But both should be 10.1. Okay, and now this gap here. Man, there's something very demoralizing of like trying to do something for so long and then keep failing. But we do have to make it walk. It just has to happen. So we have 0.3, 0.5 move face. All right, let's try this. There's gonna be a planar here. That should be 0.1. This broke. And then we gotta turn off section view, restart section view. Okay. So I think that's pretty tight. Basically as tight as it can be. So now we just print this guy. We open Bamboo. I go and turn on the 3D printer. By the way, did you guys notice how the servo horns have not failed again? It's funny because I actually printed extra thinking, oh, for sure something's gonna fail. Nothing failed ever again after the last iteration. It's been so beefy. I almost think that the servo motors would fail before, which that would suck. But yeah, we made those pretty beefy. Okay. So like that, probably not like that. How do we print this last side? Oh, I see. Okie dokes. I mean, obviously the most material efficient way is to print it this way. All right, so here we go. So I'll print it, we'll test that, and we'll be back to trying to make this thing walk. All right, so the new leg upper finished reprinted. And so I'm just gonna do a quick assembly time lapse here. Oh, it's so warm, it's always so warm. And we'll see how this works, if this fixes all of our issues. And yeah, so here comes the time. So I don't know if you'll be able to see this, but this, look, I try to move. This doesn't move at all anymore. This is perfect. This is great. So I'm gonna go ahead and print 3 more of these. Now I don't think these alone will, get us crawling, but it will definitely help. Now I also wanted to show you guys one more thing. So while I was having dinner, I actually had a conversation with ChatGPT. I was asking it, what's easier, to crawl or to trot? Obviously to crawl, but I was just setting up the context here. And then I'm like, can you break down each step needed to crawl? And everything it describes is exactly what we've been doing for the past couple hours. So I still think that inverse kinematics will help a ton here. So I'm gonna do that next, along with improving the leg uppers. But I am pretty sure that tomorrow we will be crawling across the living room. I am like pretty sure. So I'll see you tomorrow.
Tomorrow for sure.